Okay, so we did a lot of discussion on this problem. Got a pendulum that's 3 kilograms, length 4 meters, pulled back a meter and released. You hit it with a 2x4, hit a point 20 centimeters in front of equilibrium, impulse 14 kilogram meters per second. What's the equation of motion before and after the strike? Okay, challenging problem. So we break it down. First, we got answers that, well, we can find the position function. Okay? Well, yeah, you have enough information to find the position function if you know enough to do that. And find the position function, and I added from release to contact. That was implicit, the position function right after release, because we're going to have a different function after the thing is hit. So if we left it at that, this wasn't in there yet. So the next thing you would do if you had that position function is you could use it to find the velocity just before the strike, just before the thing is hit. Call that the strike. We're not playing baseball. No strikes and balls. You're going to hit this thing. Okay. So find the velocity just before the 2x4 strikes the steel mass. You could use the position function and its derivative to do that. Okay? And we got a pretty good answer there. Well, you figure out the time it takes to get to the 20 centimeter position, and then you plug that time into the velocity function, which is just the derivative of the position function. So, that's a good answer, and I'm fairly confident that that would have occurred. And that alone, this is a midterm, not a final exam, that alone would be a perfectly good passing answer, is at least a C. Okay? There's much more that can be done, especially with what happens after a thing is started. But that could be done, okay? And that demonstrates pretty good knowledge right at this point. Okay? And we could also use simple right-angle trigonometry and energy conservation. If the thing is here and released and comes down to here, its length is the same here and here. It drops from this point to this point. There's a change in potential energy. It doesn't depend on the path, so it could have been dropped from this position to this position. And you could easily enough calculate the change in potential energy, set that equal to the kinetic energy. Since it was dropped from rest, change in potential energy will be equal and opposite to the kinetic energy it attains, and get the velocity that way. And it would actually be very interesting and fairly impressive in a case like this to compare the result you get here and the result you get by using the small angle approximation involved in a simple harmonic approximation to the motion of this pendulum. 1 meter, it's not really huge. You don't get really a huge angle at that point, but it's big enough to get some discrepancy between the simple harmonic motion and the actual motion. But we don't know the mathematics in this course to analyze the actual motion. Okay, so simple harmonic is our best approximation. But it's not totally accurate, and it'll give you a little bit of difference in the potential energy changes. If you compared that, that would show some really good initiatives and some really good insight. Okay, that'd be like A-level thinking. Okay, after that, now at this point, we digressed before we started thinking about what happens when the thing is hit. We came back to the basic principles. Nobody knew what the basic premise of simple harmonic motion is. And without knowing that or knowing something about the behavior of pendulums, the restoring force behavior, you're not going to get any further in this problem. You're not going to be able to find omega. You're not going to be able to find the equation of motion. So again, for the umpteenth time, here's the line of reasoning. Net force is linear restoring force, okay, negative kx. You have restoring force constant k. There's your net force, which gives you mass times acceleration, acceleration being second derivative position, as we know, equals negative kx, which, if through some steps that I'm not going to review here. I'm just drawing your attention. You need to know them. Gives us x equals a cosine of omega t. Now, you don't really know how to prove that this is a solution to this differential equation, but knowing this, you can verify this differential equation. You have to verify that this is a solution to the differential equation just by doing a couple of derivatives. Comes right out. And this is a solution to this equation provided omega is the square root of k over m. So right there is the omega that goes into the function, and you can't do the function without that. A is the amplitude. You have a reference circle whose radius is equal to the amplitude of the motion, in this case, the radius of 1 meter. And drawing that reference circle and describing how that models the motion, even if you didn't find omega, it would go a long ways here at this stage. Okay, so the impulse momentum theorem is what you use with this, because you have the impulse of 16 kilogram meters per second, and you know the impulse momentum theorem, and somebody wanted to tell me that this was the number of joules of kinetic energy change or something. Doesn't even have the right units, so that answer is totally wrong. If you know where the impulse momentum theorem and the word kinetic energy theorem come from, at least for uniform acceleration, that's good enough right now, but you got to know the two. You got to know where they come from. Substituting A equals F net over m into one of the two equations of uniformly accelerated motion that give you alternately work energy or impulse momentum. And you should know that, because then you can always think back to the source of the theorem and relate it to what's going on, okay? Okay, so anyhow, you get a new velocity. Okay, well, you get a change in velocity from the impulse momentum theorem. You get a new velocity from that. Okay, just add the change in velocity to the old velocity, and hopefully you do that with the signs correct and all that. And now you get a different equation of motion. And not too hard to get that equation of motion. Now, solving this problem would be a good problem for a final exam. This is only midterm. So I'm not going to expect too much on this problem, but the more you show me, the better. And I would expect at least that you would know where this comes from. You would be able to find the equation of motion here, and you'd be able to apply the impulse momentum theorem to get the new velocity. Well, you then know how to use that to get the new equation of motion. Well, that's kind of the difference between an A and a B. Okay?